Thanks for everybody for being here. I think all of the presenters so far have laid out a lot of what I'm going to talk about already, or at least the building blocks. Just a quick overview. We'll talk about the motivation a little bit, some of the theory, use, applications, and work going forward. So what's the motivation? You've already seen, you can probably imagine what some of the motivation is for this approach. The lack of a general model for bold time series forces complex processing. So, just to kind of, in a sense, piece everything together that you've seen today, this is basically a workflow for, in a sense, how fMRI is analyzed. So there's several steps here that we've already covered, including retro-ICOR for correcting pulsation. How do you regress out motion parameters, or how do you deal with the CSF or white matter signals? Then we move on to the issue of what is the global signal. I think the global signal removal has pluses and minuses, but in a sense we still don't know what it is, and I think that varies a little bit with how you estimate it. Do you despike? Do you bandpass? What frequencies do you use? And then at the end of the day, it seems like a lot of the data are still so problematic that censoring is just kind of the last resort, right? So what multi-echo fMRI does, I'm just going to go through the slide quickly. What multi-echo fMRI does, it tries to ask the question, can we use the information in the T2 star decay to enhance fMRI processing and analysis? So just to give you an idea, I'm going to use this pointer over here. As you've seen so far already, that a standard fMRI acquisition based on echoplanar imaging is based on a concept where you excite the volume, and then you actually wait a while for some optimal echo time to come around, and then you image at that optimal echo time. Well, it turns out that the optimal echo time, of it at 3 Tesla, for example, is 30 milliseconds. That's actually sort of average for the whole brain, but the truth is the orbitofrontal cortex has a T2 star of about 20 milliseconds, and the motor cortex and the visual cortices have T2 star of about 50 milliseconds. So 30 milliseconds isn't optimal anywhere. It's actually just a whole brain average. So what a multi-echo fMRI, multi-echo EPI acquisition does is says, forget about that. There's no optimal single TE. Just acquire as many TEs as you can, as fast as you can. So so you pack in, you basically do a readout as soon as you can after the excitation, then you acquire another image, which tends to be around the typical acquisition between 20, 30, 40 milliseconds at 3T, and then you can acquire another image, and then and up to more, but 3. Once you acquire 3 images, you can actually do an interesting trick, which is you can essentially fit the T2 star decay at every voxel. So here's just an example. I'll go through a little bit more of this in just a bit, but essentially, given at any given voxel, given any excitation, signals decay over time. It very roughly follows a mono-exponential decay, but if you had more echoes, if you sampled more echoes, and if you had a higher precision measurement, it would basically be roughly bi-exponential. It also might have a sync decay, but this is good enough for what we want to talk about. When you have an activation over here, and you have an inflow of oxyhemoglobin, your magnetic field in your voxel stabilizes. The decay then slows down, and so at any given echo time, a measurement at any given echo time shows you a bigger signal because the decay is now slower because there's oxygenation in the voxel stabilizing the field. When you take the difference between the decay of a activation versus a decay at rest, and you just subtract, what you get is the bold contrast curve, right? So you've probably seen this before, and based on this contrast curve is how you decide, the peak of where the signal difference is maximum is how you decide, okay, this is a TE I want to acquire at. But more generally, this bold contrast curve, if you actually sample several echoes, you can utilize this contrast curve to do interesting things. So to give you an idea of the type of model we move to when we think about things in terms of T2 star this is in a sense what multi-echo ICA works from, in that after a basic image alignment step, you have the total variance of your data. In the first step, we separate thermal noise from signal, thermal noise being characterized as anything that doesn't look like T2 star or doesn't look like S0 and doesn't have any significant variance. So basically, that's our model for thermal noise, and then we have signal in the most general sense, which gets broken up into a bold subset and a non-bold subset. And all of this together explains all the variance in an fMRI data set. And the goal of multi-echo fMRI analyses, at least as we've put it together, is to essentially explain as much of the variance as possible and attribute some aspect of a model to it. So just a little bit of theory. The idea of multi-echo fMRI is to take this T2 star information and utilize it to its kind of maximum ability. So I'm going to go through these boxes, kind of starting at the top left here. So each column represents a type of change. So there's essentially two parameters that are changing fundamentally during your fMRI experiment. One is your decay rate, basically the change in your magnetic susceptibility in your voxels. Another is the initial intensity, also called the proton density. It's the amount of stuff in a voxel. So we're going to talk about the left column first. Given a change in the magnetic field properties within your voxel, as I mentioned before, you get a change in the decay rate. If you take the difference, you get a contrast curve. Now, which we've already talked about, but an interesting thing happens when you divide the contrast curve by the mean of the decays, you get a very important relationship. You find that the percent signal change of the modulation is linearly related to the echo time. So that means that if you have a change in R2 star, if you have a change coming from the bold signal, your percent signal change the magnitude of percent signal change will change linearly with echo time. In contrast, if you have a change in proton density that can be associated with motion, pulsatility, scanner artifact, you name it, so that's a change in the intercept of the exponential decays. If you take the difference of the decays, you get another exponential decay. If you divide the exponential decay by the mean of these two, you get a flat line. What that shows you is that for a purely S0 modulation, the magnitude of the signal in percent signal change units does not change with echo time. So in these kind of two boxes at the bottom, you have actually a really simple relationship to understand what's bold and what's not bold. What's bold is basically what changes in percent signal change with echo time, and what's not bold is what doesn't. That fundamentally differs from a type of discussion where you're thinking about what's cardiac or what's motion, what's scanner artifact, so on and so forth, right? So as an idea, this is the basic concept. So in addition, separate from that, a very important use of multi-echo data is contrast optimization. So here are two rows of images, one acquired at 3T, the other acquired at 7T. Each column represents a different echo time. Optimal combination is the process of, there's a few different combination schemes. There's one from Posse in 1999, which is called optimal combination. You can combine the images of different echo times to compensate for susceptibility artifacts. The reason why that works is because the reason why you have a susceptibility artifact, the reason why you have a hole in the brain, is that the signal has decayed away before you've actually captured it. And it's decayed away because the proximity to air tissue interfaces creates an unstable magnetic field, which basically speeds up your T2 star and it vanishes. But if you acquire the image at an early time, you can actually sample that signal. And then by estimating T2 star at every voxel, which you can do, and then combining it using that as a weight mask, you can actually recover orbitofrontal cortex, inferior temporal regions. And this plays out at 7T as well, and it's even more important at 7T because T2 star is even more varied at ultra-high fields and is basically more 7T systems hit scan centers. This will be understood kind of a little bit more, that higher fields equals more variability, but with a multi-echo approach, you can compensate for many of the issues related to that. So how does this work? So we're going to go back to the story of the line and the story of the two lines, the slope versus the flat line. So what I said before is that if you have a functional change, a bold-related change, the percent signal change of the effect will scale linearly with echo time, right? Whereas if it's an artifact, percent signal change will not scale linearly with echo time. So let's say you have a component here. This, I think you'll agree, represents something brain-like. It has a slow time course. If you fit the model time course to the individual time series of the different echoes and express it in percent signal change, what you'll see, as represented in this particular figure here, in these two figures, is that the areas where you have significant bold signal, percent signal change will increase linearly with time. So this map is actually, even though these maps are fits of the voxel time series to the model time series, this map is the fit of 3 points to a line. Yet it's really clean. That actually shows you that this effect called TE dependence is extremely strong, right? So you need very little data to actually see this TE dependent scaling. If you then use these two to make a statistical parametric map, you can basically see that the places in the brain where the effect is scaling with percent signal change basically maps onto the bold model. In contrast, if you do the same fitting procedure for voxel by voxel, fit the percent signal changes to this model, which is the kind of no change model, you get a flat map. You get no loading onto the non-bold model. Take the opposite case. If you take a ring around the brain type component over here with this kind of pulsatile component time course, you see that these modulations with echo time do not load onto the R2 star model, but do load onto the S0 model. So visually, you can kind of see the rationale for how you, in a sense, you don't really, strictly speaking, need to look at where the components are localized or what their time courses are. A major amount of information is gained from actually looking at how the effects scale with percent signal change. So the kind of summary picture looks like this. Kind of in addition, we don't want to look at pictures of what loads onto what. The effect is sufficiently strong that we can kind of come up with a pseudo F statistic to describe the kind of component level weighting per effect. So you have a component level weight for bold weighting, we call kappa, which is just a pseudo F statistic. It's the scaling coefficient, it's the goodness of fit weighted by the magnitude, and you get the same thing with the artifact weighting. These things kind of reduce to two metrics called kappa and rho. So for bold effects, you get essentially very high values of kappa and low values of rho, which correspond to the bold effect, the percent signal changes of the bold effect loading onto the R2 star model versus the percent signal changes of the artifact loading on the S0 model. So how does this play out over an entire decomposition? So given a 10-minute acquisition of an individual subject, the multi-echo ICA decomposition in this particular case gave 130 components. If you then go component by component and compute the kappa and rho of each component, then render the kappa values as a scree plot, as just a descending rank ordered kappa value, you see this red line here. And then for every one of those components, if you plot the corresponding rho value in blue, you get this plot. So basically for this particular component, which is like 53 or whatever, this value of kappa corresponds to this value of rho. So from this image, what you can actually see is two regimes of components emerge naturally from the data. So you have one regime of high kappa, low rho, and another that's high rho and or low kappa. So there's a natural splitting of the data. What does that look like when you actually render the bold components? These are the kinds of, basically the high kappa components. If you render them as maps, this is what you see. At the individual subject level, you get a relatively rich representation, motor cortex, lateralized motor cortex, critically putamen, thalamus, visual cortex, and so forth. So you get the fact that we got a high dimensional representation of components at the subject level also comes from the fact that we've combined the echoes early on, which also increases contrast to noise, which I haven't talked about here. But there's a general benefit of higher dimensional representations of functional activity, as well as automatic detection of the functional components. So more recently, we've been able to implement multi-echo, multi-band EPI. So just to give you an example, there's several variants of the sequence. The sequence that's been implemented by the Minnesota group, it's now a part of the HCP standard sequence, so you could just dial up the number of echoes and you'll have a multi-echo data set. What you can achieve is 2.5 millimeter, for example, 2.5 millimeter isotropic resolution with a multiband factor of 4 gives you a TR of 0.87 seconds using in-plane acceleration 2 and gives you can for 3 TEs. So what does that kind of boil down to? The contrast on these images is not too bad. Okay, so as you can tell, Even with a multi-echo, multi-band sequence, the same story plays out, that as you go to higher and higher echo times, this is kind of TE equals 30, as you go to higher echo times, you get more and more dropout because the point at which you're imaging doesn't have any signal anymore because it's dephased away. But if you actually use these images to estimate, you can actually use these images to estimate a T2 star map as well as an S0 map. So the T2 star map shows you highest intensity in the CSF. This is actually just by fitting T2 star, you get a good estimate of tissue, different types of tissue you have in the brain. And then from the S0 map, that's actually a quail sensitivity map. It tells you basically what parts of the brain or what parts of the head are overbright. Combining all this information, you can create a T2 star weighted combination, which on average tends to double your SNR. This is published in this paper and other papers that we have on the topic. Again, this plays out at 7T really well. So this is a whole brain acquisition at 2.5 millimeter isotropic resolution at 7T. You actually can see you have good hippocampus and amygdala coverage. The orbitofrontal cortex doesn't suffer high dropout. You have cerebellum brainstem coverage. So it kind of takes us closer to a turnkey 7T fMRI. Another nice surprise that we got from the 7T data is that we actually got rich subcortical component representation. So just from again another 10-minute scan of an individual subject, ventral striatum, dorsal striatum, thalamus popped out as individual components. Because we don't impose any restrictions on what a human brain is supposed to look like versus a primate brain versus a rodent brain, this basically is generalizable. It applies across species and it applies across field strengths. So this is from our paper from 2014 where we applied pretty much exactly the same method at 11.7 T in a rodent. And based on, this is kind of my favorite figure, from a single 20-minute scan of under isoflurane anesthesia, you get a representation of rodent rat networks without any magic applied that shows you cytoarchitecture that's pretty consistent with a Paxino's atlas. Just to kind of give you a view of how to use this. So the workflow goes as such. You acquire a multi-echo EPI data set. Sequences are available on GE, Siemens, Philips, and Bruker. Siemens, as I mentioned before, just comes stock with the HCP sequence. So as soon as you get that, you have multi-echo. GE sequences are available, I think, will be available from the vendor. Philips, Philips is capable of multi-echo stock. Bruker's capable of multi-echo stock. A lot of the initial work on the Siemens sequence was done by the Donders group. And then you basically take the DICOMs that come out of your multi-echo scan, you feed it to DICOM to NiftyX, which you might be familiar with from MRI cron. It spits out separate TE data time series. This goes into our fully automated tool distributed with AFNI called Mica.py, and it handles pretty much everything. Multi-echo preprocessing, it does the T2 star weighted combination, it does a spatial ICA incorporating the T2 star and S0 info, it does the component selection, and then spits out time series. And then you can take your bold time series and feed it into your favorite toolbox. And so we've tried to automate this as much as possible. All that being said, it's important to look at your data, as all the other speakers have mentioned. So I'll go through the outputs in just a second. Critically, I'm not going to go into detail here about why this decision was made, but no full width spatial smoothing is applied by default. And there's no bandpass applied by default because basically the super low frequency nuisance effects are non-bold. As are the high frequency effects. So they just come off in the denoising. And no spatial smoothing is applied because for several reasons. One, it reduces, it kind of screws up with the component detection ability. But more down the line, spatial smoothing actually hurts your ability to do cluster level inference for small brain areas. So this is one of the areas, you'll see a couple of results on this in just a bit, but it kind of helps us. There's a graphical user interface, which is available on this website. So you basically punch in your TEs, your data sets, your anatomical, you hit start, and it basically does the process that I mentioned before. There's also a report generation capability. I'm going to skip over this for lack of time, but I'm just going to show you a video. similar to the videos you've seen already. So this is a raw data after optimal, raw fMRI data after optimal combination, but after removing the mean, right? So you're not seeing the nice, pretty mean image, which you delete anyway. This is the, essentially, this is what raw fMRI data looks like. After isolating the non-bold noise, this is the time series you get. And what actually shows you is the non-bold noise is actually a relatively simple combination of a high-frequency pulsation and a jump, right? So if you subtract the first data set from the second, if you just subtract the first data set from the second, this is the resulting data that you get. You can actually see the networks evolving over time as a movie. So it's almost like instantaneous correlation with the limit of delta t going to 0. Okay, so just a kind of comparison of ideas. The HCP approach versus the multi-echo, multi-band approach. The HCP approach is focused on resolution. They push, to 2 millimeter, 1 millimeter resolution when they can. The multi-echo, multi-band approach tries to go towards sensitivity, tries to go towards versatility. In general, the recommended HCP scan time is about an hour. But the multi-echo, multi-band, we try to get maximum sensitivity within 10 minutes. This is applicable for both task and rest, the multi-echo, multi-band approaches, and it scales across field strengths. And of course, there's no training. There's a good study by Ottavia Di Pasquale where she compared multi-echo fMRI denoising methods in an ADHD study comparing healthy controls and ADHD patients. In these different correlation matrices, what we see is that comparing across all these different correlations, multi-echo ICA attenuates residual correlation equivalently for ADHD and healthy controls, whereas that's actually not true for several of the other methods. Several of the other methods either do not clean the data equivalently, or they neither of them clean the data particularly well. Here's just a dual regression map of, by the way, this is acquired at 1.5 T. If you look at the dual regression maps of the default mode network, multi-echo ICA at 1.5 T is the only one to find the hippocampal contribution to the default mode network for both healthy controls and ADHD. Just give you some more applications. A really important study by Mike Lombardo and I, we wanted to see how multi-echo ICA would perform in task in the mentalizing domain. And we used two tasks. One's a other mentalizing task, and other's a stories task. They're both in block design, and they're both comparing two contrasts. What we find is that effect sizes were generally increased in the multi-echo fMRI analysis. So I should mention, we compared multi-echo ICA to GLM denoise as well as to the optimal combination and motion regression. Comparing all these three, based on a very large reduction in intersubject variability, we found that the number of subjects required to get to 80% power across brain regions ranging from DMPFC and cerebellum and VMPFC were roughly half. So given essentially, if you wanted to find a significant activation at 80% power in DMPFC, where you'd need 45 subjects, you can actually do it after just taking the same data but analyzing with multi-echo ICA in half the number of subjects. And this kind of played out through most of the regions, or all the regions actually. Some of the regions were kind of equally bad. Another capability is because we don't apply any bandpass filter to the data, we can actually find activations related to task in any design that we want. So we don't necessarily have to impose a 20-second or 10-second alternating block design. We can actually do long blocks and short blocks, sigmoids. This is actually really important for pharmacological studies because we don't know what the time series shape should be. So it's just an example. The task here was a flashing checkerboard with varying contrast. And the multi-echo ICA approach was the only one to be able to find the sigmoidal change and disentangle it from a monotonic drift in the non-bold series. Javier's recent paper on fast event-related and cardiac-gated task fMRI showed that multi-echo ICA had essentially the highest rate of event detection. The t-statistic and the highest t-statistic, even though you had a small reduction in effect size in the optimal combination, possibly due to T2 star extents, T2 star effects. The activation extent was also highest in multi-echo ICA. Laurel Morris used basically multi-echo ICA analysis of multi-echo data to map the subcortical correlates of cortical areas. So she basically seeded pre-SMA, SMA, and VMPFC, and using a seed-based correlation approach, actually mapped the striatal correlates of these regions, which then was also mapped to the layout, the correlates of these cortical areas in substantia nigra and VTA, which, as you know, is a tiny area. In comparison to a probabilistic reversal learning task, also showed that connectivity scales with performance. Our paper, Mike and I also worked together, led by Rich Bethlehem, to show if oxytocin changes functional connectivity, and using a dual regression approach, we found using multi-echo ICA a very strong shift in oxytocin-related inter-network interactions. So essentially you had a increased interaction between the insula network and the subcortical network. And then finally, this is actually one of my favorite kind of findings, is in the context of neurodevelopment, asking the question, is the number of bold components the same? Is it constant across age? Is it a random effect? We find that it's not. Actually, the number of bold components decreases as a power law with age. This is something you can kind of only do once you have a model for bold components that doesn't depend on any particular template set. And I think this is in review right now, but I think it'll have some consequences downstream. So future directions, we've also implemented, actually we haven't, Cohen et al., along with GE, have implemented simultaneous multi-echo multiband with PCASL. Conclusions, so MICA utilizes multi-echo fMRI acquisition to enable fMRI analysis with a T2 star decay model. The benefits are it simplifies fMRI preprocessing across experiment types. It reduces arbitrariness. So we don't need different pipelines for resting state and task. It's one pipeline for all types of data, or as many types of data as we've tested so far. It enables high-quality fMRI denoising without scan-specific training. It increases, and it's applicable to both human and animal. Obviously, our best success is with human, but we have promising results from animal, as you've seen. Some limitations are there's some nominal cost in resolution, but our effective resolution is still good because we don't apply spatial smoothness, and then we're also utilizing multi-band. But more work is needed to compare MICA to other acquisition types. Thanks.
Okay, thanks very much, Prantik. Any questions for Prantik here? One over here.
Hi, thanks. Just wondering, you showed all the networks that you get out of MICA. I'm wondering, do you see other components that may not be so neural in origin?
Oh yeah, you got loads. I mean, I only showed the bold ones. But the types that you get under the non-bold regime include cardiac pulsation, drift, loads of head motion, and also grap artifacts, acceleration artifacts. Those are all kind of under the non-bold regime.
So you don't see those at all?
They're not included. They're non-bold, so they basically they're not included in the bold time series. So we basically just project out the entire non-bold space.
Okay, maybe I misunderstood because I thought you ran ICA on your after separating the time series.
No, the ICA was applied on the raw data, and then we used the non-bold components to project them out.
Sorry.
Yeah. Okay, one last question.
Hi. Because some of the respiratory artifact is also accessibility dependent, so how would the multi-echo deal with that?
So we actually I didn't talk about this, but the MICA pipeline actually computes a vein map. And the way it does that is because the draining veins have low T2 star because they're filled with deoxy blood. And so the vein map is actually estimated directly from the EPI data, and the vein map is used to identify those components and remove them.